Hello students, today in this lecture session we are going to discuss more about the energy and momentum of an electromagnetic wave. First, we shall write the electric field as E equal to E0 into cos of kz minus omega t plus delta. Now you are all familiar with all these terms, but I'll just briefly go through this. So here we can say this k can be called as the wave vector or the propagation vector. Can be called as the wave vector or propagation vector. Okay, and that is which is directed in the direction of the propagation of the wave. And you know that this is the equation of the electric field written for a wave which is traveling in the z direction. So this is the z is the direction of the propagation of the wave. And we know that, or we have understood that, the electric field will be perpendicular or oriented perpendicular to the direction of the propagation of the wave. So if this is the propagation of the direction z, then obviously electric field will be lying in a plane in either in a x or in a y plane, but for a y direction. Okay, for the time being, let me consider this electric field is directed in the direction of say x. Okay, let this be x, and the unit vector in the direction of x is denoted here as n, and the unit vector in the direction of the z is denoted in our study as k. Okay, so you just remember that unit vector in the direction of x is n, unit vector in the direction of z is k. It is not the wave vector k, it is the unit vector k. Okay, so that will be always represented by a cap over k. So thus this is the equation of a electric field vector whose where the wave is traveling in the z direction, and you know that this delta is the initial phase of the wave. So sometimes this delta need not be there need not be a delta, it can be 0, but generally when I write the equation with the initial phase written. Okay, so now I can write the electric field magnetic field B as equal to B0 into cos both of them in the same way, that is cos is kz minus omega t plus delta. But you know that electric field, or we have already understood that electric field vector and the magnetic field vector are exactly perpendicular to each other. It should be like that. If this is the electric field vector, then obviously magnetic field vector B should be in a direction perpendicular to both E and Z, right? So that means the direction of the B should be perpendicular to N and K. So perpendicular to N and K is actually K cross N or K cross N. Okay, so I write this direction of B as equal to K cross N. Okay, so the electric field vector can be written like this, the magnetic field vector can be written like this. Okay, so then I can write these equations as equation number 1. So these are the preliminary equations for E and B, which we already know. Now we have already understood that the energy density, okay, energy per unit volume, energy density or energy per unit volume stored in an electromagnetic field, EM field, has been found out as equal to U, which is equal to 1 by 2 into epsilon 0 E square plus 1 by 2 mu 0 into B square. This also we have understood in the section where we discussed about the Poynting's vector. Okay, so this is the energy per unit volume stored in an electromagnetic field. This is the portion of the energy which is contributed by the electric field, and this is the portion of the energy contributed by the magnetic field. Okay, now we had proved in the previous class that numerically this magnetic field B is 1 by C into E. I hope you remember that this we derived from the relation that we del cross E is minus dou B by dou T. So by applying this, we have finally arrived at the relation that B is 1 by C times E. So I can obviously say B square as what? B square is equal to 1 by C square into E square. Okay. Now you see what is 1 by C as per according to or with the in relation to the permeability and permittivity of free space. You have learned that C is 1 by root of mu 0 epsilon 0, right? So I can write C square as what? C square is equal to 1 by mu 0 epsilon 0. So I can write instead of 1 by C square, 1 by C square can be written as mu 0 epsilon 0 into E square. Okay. Now, okay, so that much we understood. Now let me consider this as the equation number, say then this let it be 2 and let it be 3. Okay. Now we have already defined this as the energy density, right? Half epsilon 0 E square. Now see B square is, we have found out B square as equal to mu 0 epsilon 0 E square. So then the contribution of the and the total energy density as part of contributed by the magnetic field is 1 by 2 mu 0 B square. I'll just find out what is 1 by 2 mu 0 B square when I substitute this instead of B square. Okay, let's see that. 1 by 2, a part of this U energy density which is contributed by the magnetic field is 1 by 2 mu 0 B square. And we have found out that B square is equal to mu 0 epsilon 0 E square. So this is mu 0 epsilon 0 E square, right? So that is mu 0 will get cancelled. That is 1 by 2 epsilon 0 E square. It's interesting, right? Because the contribution to the total density, energy density, contribution by the electric field is 1 by 2 epsilon 0 E square. And numerically we have found out that the contribution to the total energy density by the magnetic field is also 1 by 2 epsilon 0 E square. So what does that mean? Yeah, it means that both electric and magnetic contributions are equal to the total energy density. So I can say that the electric and magnetic contributions to energy density of an EM wave, right? Energy density in an EM field, electromagnetic field, are equal. Both of them contribute equally to the electromagnetic field. Okay, so then I can write U as equal to U, the contribution in U by E and contribution of U by B. So both of them are same, and one of them is half epsilon 0 E square. So half epsilon 0 E square plus UB is also found out to be half epsilon 0 E square, half epsilon 0 E square. So then I can write it as equal to epsilon 0 E square. Okay, and now let me substitute for this E square, which I have written already E in this form, right? So I am substituting this E there. So I can write E square as E0 square into, okay, cos square kz minus omega t plus delta. Okay. Now, so let it be this equation number 4. Let it be the equation number 4. Okay. I can say that as wave travels, this is the energy density stored in an electromagnetic field. Now, as the electromagnetic wave travel, it carries this energy along with it. Now, we have already proved that the energy flux density, okay, that is energy flux is energy per unit area per unit time. Energy flux density transported by the EM wave, transported by the electromagnetic wave is can be written by vectorially, or that is actually the Poynting's vector, and this was found to be equal to 1 by mu 0 into E cross B. Okay, you have already derived that. That is 1 by mu 0 into E cross B. So I have derived I have written the formulation for U. Now I am coming to the Poynting's vector A S, which shows the energy transported by the electromagnetic wave, which is actually 1 by mu 0 into E cross B. Now I have to write what E cross B is. That is easy to understand. You know that now what is E, right? E is E0 cos kz minus omega t plus delta, and B is actually the same thing, but then B0 into cos omega t minus, B0 into cos kz minus omega t plus delta. Now I want to find E cross B. How can you find E cross B? You can try it. It's very easy. Just find the cross product E cross B. Okay, so you know how you do that, right? What you normally do is you find using matrix. So you can find I, J, K. Then you write, you know that electric field, suppose that we have considered here electric field is in the direction of X. So I can say this as E0 cos into this kz minus omega t plus delta, and there is no value for J, no value for K. Okay, that is, there is no electric field in the direction of J or K. Now similarly you have magnetic field in the direction of J, not in the direction of K or X. So I can write magnetic field here as E0, then here you write as B0 cos this content which we have, cos is a kz plus omega t plus delta, and put here 0. Then you find this I, you can find this E cross B value. You find I into, this will be 0. Then you find J, take J, multiply this to that all term will be 0. Then you will only have a vector or component in the direction K, right? All the other terms will get cancelled, and we obviously know if E is in the direction of I, B is in the direction of J, obviously E cross B will be in the direction of K, right? So then you will have a component K, which is E0 into B0 into cos square, obviously that. So I can write this Poynting's vector as 1 by mu 0, 1 by mu 0 into, okay, then E cross B, as we have found out this way, it is actually okay, so that is E cross B is E0, right? Then B0, okay, then cos square into KZ, cos square KZ plus omega t, KZ minus omega t. As we have written kz minus omega t plus delta, right? Now we have found out what is B0. B0 is found out as, what is B0? B0 is B0 is 1 by C E0. I can write B0 as 1 by C E0. So I can write it as 1 by mu 0 into 0 into 1 by C into E0 cos square kz minus omega t plus delta. Okay, then there is E0 square. Then what is C square? C is found to be, or I can say that C is actually 1 by mu 0 epsilon 0. Okay, or C square. C is equal to root, C square is 1 by mu 0 epsilon 0. Then I can write 1 by mu 0 as what? 1 by mu 0 is will be C square epsilon 0. So then I can substitute for 1 by mu 0. Then this becomes C square, okay, then epsilon 0 then E0 square divided by, there is another C in the denominator, cos square kz minus omega t plus delta. Another C is there that you can one of the C you can cancel. So finally this equation becomes Poynting vector S is becomes C into epsilon 0 into E0 square into cos square kz minus omega t plus delta. Okay, very interesting, right? So now what is this epsilon 0 e square cos square kz minus omega t plus delta is what? Just see here. What is u? Epsilon 0 e0 square into cos square kz minus omega t plus delta is u. So then I can substitute for this, right? So I can write C and this part is actually U, and when you write it as in the Poynting vector, and this is in the direction of Poynting vector is in the direction perpendicular to E and B. So perpendicular to E and B is the direction of the propagation of the wave, and that is the direction of Z. Okay, so this becomes Z. So Poynting vector S is actually equal to C into U into Z. So S is actually, so what is S? The Poynting vector S is actually energy density. This U is energy density, right? So energy density times velocity. So I can say that S, which is the Poynting vector, is basically energy density times velocity. Energy density times velocity. So that you have to remember, that is S is equal to C into U. S is equal to C into U. That is energy density times velocity is actually the Poynting vector. Thus I can say that the energy transported per unit area, okay, per unit time by electromagnetic wave is actually equal to C times the energy density U. Now we are coming to the momentum. Okay, so this is we were talking about the energy of electromagnetic wave, and energy transported by the electromagnetic waves is C times the energy density. Okay, that we have understood. Now you come thinking about momentum. Do electromagnetic waves have momentum? Obviously yes. As you normally say in the case of a particle where momentum is equal to mass times velocity, here we don't have any mass, but then anything which have energy E, okay, then we'll have momentum P as E divided by C. So, okay, so the energy divided by the velocity of the light, here electromagnetic wave, the velocity is actually C, and this is actually the momentum. So obviously electromagnetic, even though it doesn't have any mass, obviously since it possesses energy, it should have momentum. So it's very important to study the momentum of an electromagnetic wave. And this momentum density stored in electromagnetic field, let me say this is actually P, and this is actually equal to S divided by C square, where S is the Poynting vector. Okay, now for a monochromatic plane wave, we know that momentum P is equal to, as per we have already derived what S is. S is actually equal to C epsilon 0 E0 square. I can substitute the whole thing here. So I can write it as 1 by C square, that it be there, that is this 1 by C square, then S is C epsilon 0 E square into cos square, okay, kz minus omega t plus delta into z. Okay, so this C and 1C will get cancelled, so then I can write this, the whole thing is actually the U, energy density, which you have already familiar with. We have derived it. E is this much, epsilon 0 E0 square cos square, the whole term is actually the U. So I can write now this as equal to u divided by c, and it is in the w, obviously in the direction of z, that is the wave, direction of propagation of the wave. So the energy is transported in the direction of the wave, propagation of wave. Also the momentum is also transferred in the direction of the propagation of wave. So that is the momentum vector. Okay, now we normally we know that this momentum is actually, or u basically is a cos square factor. So this with the time, as time goes on, it actually fluctuates in the according to cos square relation, right? But then macroscopically, when you actually when you assess the momentum or the energy or Poynting's vector, everything, when you macroscopically analyze, you know that we are not bothered about the small fluctuations which we cannot measure macroscopically. So macroscopically we are or we can say that practically we are more interested in the average terms. So what you have to do is you can average. So momentum, when you say, or the energy density, when you say what I'm interested in the average energy. Okay, so that is average energy. U is what? You just see what is U. U is epsilon 0 E0 square cos square kz minus omega t plus delta. So when you average it for a complete cycle, so when you average it for a complete cycle, then you are averaging it for the whole time period 0 to t, right? So when you average it for the complete cycle, then you have already studied what is average of cos square, or you can just find out the average of cos square. It's very interesting. Average of cos square anything. So let it be x over 0 to t. You just find out what is it. You can replace this cos square x with the trigonometric relation cos square is actually cos square cos 2 theta. Cos 2 theta is, so the momentum carried by the electromagnetic wave for that time S will be equal to average energy, average momentum, then over, it is actually falling on an area A over a time, P times area into C times delta T. Okay, so that is the momentum transferred for the time C delta T. So it is falling on an area A. Okay, so the total momentum transferred is actually this much. Now I can say, let me talk about the, okay, this I just said. So then the radiation pressure, about the radiation pressure, radiation pressure is actually force acting per unit area as always, right? And this, and what is this force? That is rate of change of momentum, right? That is the change in momentum with respect to time. So that change in momentum with respect to time can be written as delta P delta T, right? Change in momentum with respect to time over A area. Okay, and you have already found out what is delta P. So that is average momentum P multiplied by area into C into delta T. Okay, that divided by delta T into area. So this will get cancelled, this will get cancelled. So then finally I will get it as average P momentum into C. Okay. Okay. Now in the previous slide, or we have derived what is the average value of this momentum, that is 1 by 2c epsilon 0 e square. If I substitute that, this is equal to 1 by 2c into epsilon 0 e square into c. So this will get cancelled. So this is actually equal to half epsilon 0 into e square. And what is this? Half epsilon 0 square. What is the energy density? Energy density was, okay, that is the Poynting's vector S average value is actually equal to the energy density I. So if you look that will be in terms of I can write it as I divided by C. That is half C into epsilon 0 E square was the energy density. So then I can write it as the radiation pressure as equal to that is radiation pressure. Don't miss, don't get confused with the momentum. This is actually pressure. Okay, it's pressure. And that is I by C. Or I can say that the energy pressure is half epsilon 0 E square. Or I can say that it is equal to the intensity I divided by C. Okay, so this is all we have learned in this session, that we were focusing about the discussion on the energy of the electromagnetic wave, then the momentum of the electromagnetic wave, then we also discussed about the radiation pressure. So thank you very much for your patient listening.